and this is not working. Now, what this whole thing about systematic evaluation and validation essentially states is that whenever you do some experiment, you are experiment in terms of you have trained a network and then you are essentially going to use that for inferencing something. Now, that will have its own variations in performance over unseen data, and that's essentially what is our validation set for all practical purposes. Now, these variations can, and the only reason for these variations to happen is because the network essentially has a different weight configuration. So, if I train it n number of times with different initial condition, then every time I am going to get a different performance coming down over there. That's what we are on a common ground with. Now, the issue is that if this performance is going to vary over every single time I am going to train this model, then what is the order of variation of this performance is what is really critical when you are trying to design a commercially deployable system. So, now the question is something like this, that does it vary in the range of 10%? What that would imply is that for one of the models trained on the same data set, my accuracy is 80%, for another model it is 90%. Now, the question is then how do I find out which model is of the best accuracy? This is one of the questions I would love to solve. Next is, if there is this 10% scale of variation in performance on the whole field of accuracy, then now my question comes down as how reliable is this model? So, if there is one model which has a 10% variation, another model which has a 2% variation. So, which one are you going to choose if I ask you this question? There are two networks which are trained using same kind of experimental configuration. One can have a variation in the order of 10% in its performance, another will have a variation in the order of 2% in its performance. Which one will you choose? It depends on what? It depends on the range in which this 2% or 10% is there. So, essentially if I have a 10% variation as well as a 2% variation on an average accuracy of say 85%, then I am going to choose the 2% one. Okay. But then if I have something like where my 2% accuracy is varying at 60%, but I have a 10% variation in 85%, then I am going to go with that one. So, you can come down with something which is called as a coefficient of variance, and I believe most of you have some idea, which is sigma by mu. It's a standard statistical term, or it's also what is called as the Weber's standard ratio. So, there was this guy Weber who had something called as a Weber's law, which you had studied in I don't know, 6th or 7th standard science. Huh? Weber's law. Weber's law. Weber's law was like the intensity of the pain which you feel, the difference between intensity of the pain which you feel is dependent on how much pain you are feeling. Or basically like how much is the difference between two shades of gray which you can perceive based on what is the amount of lightness present. And this is a very fundamental thing in class 6 science. If I have read, then you guys have also read, and they have not modified the syllabus as such in NCERT for the last 15 years. So, it does not vary. You can just Google it up, like Weber's law. So, Weber's law is a sort of a very interesting thing which always plays a role, and that mathematically is quantified in terms of that coefficient of variance. So, here that we have this whole point of basically designing a vision based system in order to characterize and then classify numbers. So, here our variation essentially is going to come because of this one. So, you can see if you look across any given row on all the columns, you would see there is a variation in how this 3, 4, 5 they will appear. So, sometimes they are thick, sometimes they are thin, sometimes they are left inclined, sometimes they are right inclined, sometimes center inclined. So, there are these plus there will be like how you have this kind of a stroking pattern. So, some of them have this kind of a circular stroking pattern, some have very straight line kind of a stroking pattern. If you look at 4, if you look at 5, you will be able to see. Some people write down 5 without any kind of a, say over here, this is without any kind of a discontinuity. But then if you look at these kind of numbers, you would see that there is a discontinuity. There is this and then this one which is done. So, there are these whole lot of variations which will start coming in, and your network which is by virtue of, if we consider that to be a CNN, then your convolution kernels are going to be appropriately tuned in order to do that. And this is what is going to cause a major problem. So here the essential point is that this guy, how good is this guy, is what we really need to find it out. Now when you want to do that, so I have a lot of things which would relate more with medical, and that's because it's sort of like a playground where I do most of my work, but then these extend over to any sort of analytics in real world itself. So if you are doing anything beyond the toy example of just looking at digits written with handwritten scripts, then now you would be exposed onto something like weather patterns, you will be exposed onto surveillance video, you would be exposed onto satellite images, you would be exposed to say military grade surveillance, and each of them are going to have the same kind of a nature itself. Now what we really need to understand is what's your playground on which you are essentially going to do all of this, and playground means that what is that real field from where all of this data is going to come. That has a very critical role. Now if you have trained a model to do something based on Indian data, directly extending it onto an African data or a European data is not going to work out, and that's for the very simple reason that the statistics of whatever you are seeing over here is very different from statistics over there. Okay, as an example, so how many of you have been in Europe? Few hands. How many of you have been in Singapore or any of this Southeast Asia? Okay. How many of you have been to Nepal, Bangladesh, Sri Lanka, Pakistan, Afghanistan? Bhutan also qualifies. To a certain extent, northeastern 7 sister states will also qualify. No, that's basically to get you to this whole point that if you are looking at building say face detectors, you are looking at average height classifiers, you are looking at building gender classifiers by looking at just facial images, then the major problem is that there is a wide scale diversity in how people appear, which is going to be there. Now if you build up a sort of age predictor or a gender classifier or something based on whatever data is available over here, and you try to take that and apply it in Bhutan, apply that in any of the 7 sister states. In fact, there is a huge variation across the 7 sister states itself. So out of my spending a good amount of time across 4 of them, I have seen they vary significantly. Then if you take it over to Europe, then it's not going to work, and in fact like Europe itself is a large scale variation which will come down over there. In Africa nothing is going to work, whatever you build over here, because it's a there's nothing of laughing. I mean, it's a very standard thing. It's a very different genetic pool over there, and by virtue of that, the whole variation is there. Plus, there's this whole issue of height to weight variation, which is of a very wide spectrum, which you get down in the whole African continent, which you will never be working out. Interestingly, what might work out is that a gender detector or a age detector which you train based on the average Indian population would very effectively work in most of the Central American and South American states. Most Brazilians would also look like Indian. I mean, that's a very common thing which happens around with my South American friends when they come over to India. Most of them, like going around in tourist places, they would just not acknowledge that you are not somebody from India, who is not of an Indian origin and who will not be able to speak any of the standard languages which otherwise is expected to be spoken in India. So these are issues which will come down. Now there are points of how you look into it. One is that whenever you are trying to build some systems over there, one basic necessity is that your data needs to be anonymized. Okay, so this is more from the perspective of collecting a data, but sooner or later, if you are deep diving into the research in this particular field or trying to, there can be two kinds of research. One is that you are trying to do a fundamental research of building a theory. The other one is that you are trying to do an applied research of building a product. Now, in this second case of applied research of building a product, one critical point is that you will be limited to acquire a data set, a very good quality data set over there. Most data sets will not be available offline or online or somewhere on the public domain. Even if you have it available, the quality of these data sets are horrible. That's from any practitioner who really does a deep dive knows that the quality of the data set in terms of annotations is bad. So you will have to really work out. Now over there, a critical part is anonymization. And in fact, you might have heard about this whole thing of GDPRs. the general data privacy regulation passed in the European Parliament. So India is also putting out a similar kind of a thing, which most likely in the next 2 months would also go out. And in fact, like our data privacy is much more comprehensive, because it's not just data privacy, it's essentially data, AI, ML, it surrounds this whole gambit over there, and it's part of the AI roadmap, national policy on artificial intelligence roadmap, which the country has as of now. That brings me to an interesting point. Maybe it's a good idea that you guys can also, as a sidetrack from your normal studies, look into the AI roadmap of India, because that will really help you in understanding where the whole country is thinking of going in terms of it. What are the next deployments where it's coming? So if somebody is really enterprising in spirit and you want to start your company, then you know where your next client is going to be, and that's in the government in some sector. Then what is your sector is what that document lays out very good. Next is, whatever you are acquiring over here, they need to be of some sort on the same modality, which essentially means that if you are training face detectors to work on SLR kind of images, very high quality images from your DSLR cameras, then please do not expect that your face detectors or any of those engines are going to work on webcam images. That will just not work, and that's one thing which you will have to take. Next is, if you are training some model to work on camera images, don't expect that they will be working on X-ray images or satellite images until and unless you are retraining that model. The model in vanilla is essentially the architecture plus your weights. They will not be working over there. So everything needs to come from whatever is your modality or your set over there. Next is that this is something which is very specific to medical images or any sort of a healthcare data. But then if you are trying to build something with say psychological markers, something for biomarkers, then you will also need to keep that same thing, which is, one is that whatever are the classes of objects or classes of things which you want to classify, they need to be of the same sort. So essentially, if you are trying to build cat versus dog detector, then you need to have the whole range of all cats which are visible, range of dogs which it can encounter, all of this, otherwise it won't work out. And in fact, like this is something, if you go back to the first class where I was dealing about the data sufficiency and statistical sufficiency cases, we did understand that if there are missing samples over there, then the Bayes equation is something which becomes unsolvable, and that's one of the reasons why none of your networks or anything will be working, because it has not seen a similar class or a similar granule of data ever available. Next is something from your face recognition, and everything will also have the same thing, which is that they need similar genetic makeups. So this is the point of saying that if you are training a detector on the standard North Indian faces, then it will not be working on Southern Indian or Northeast Indian faces over there. So you need to keep all of them. Now if you want to do a face detector on all pan-Indian faces, then please get to all the states, get to all the genetic pools, and in fact covering all the states might not get you all the genetic pools. The genetic makeup is a very different thing. And that brings me to another interesting project which the country currently has, which is called as Genome Poetry. Now Genome Poetry is something which is a CSIR labs initiative. So it's a big data analytics lab at Bangalore and the Institute of Genomics and Informatics and Integrative Biology at Delhi, which do it together. And that's interesting. So essentially, like you have an Aadhaar as of today. So the idea is to have your whole gene sequence done and kept down with a digital identifier over there. So the next time when there is a keen search or something, so essentially the point is that if you meet in an accident or something and nobody is able to really recognize you, but from any of your body fluids or living tissues, you can do a gene sequencing and find out the primary signature, and that can be used as one of the final identifiers for doing it. Now what that would need is that every single individual in the country will have to be gene sequenced. Now there can be pros and cons. There are people who would go against that, but then barring the fact that yes, there are risks involved because your identity, your final key is something which goes to the government, but then now you need to trust into believing something like who is the government. That's essentially the people of the country who make it up. So if you are not going to be unethical, then that also does not go into it. But these kind of large projects which are getting done today is on creating these bigger data sets, which tomorrow are going to be the biggest fuel source for any of these data science models, any of AI models which we are going to build up. And there, this is one big thing which it's going to really enable. So tomorrow if you want to build a face detector which has to be gender agnostic, or you want to come down to something like by looking at a face, can I find out somebody's skin? So who are their parents, who are their siblings, and who are their successors over there. If I want to do that, then you would need a ground truth information, which is either the person comes and says that, okay, these people are who are family, or otherwise the other option is that you have a whole genetic makeup over there. Because by and large, by virtue of migration, families have split and they have gone in a lot of places where you would see that a family had split somewhere 3-4 generations ago, and they are possibly not even aware of each other being their kins on a extended family, but then because of this whole genetic sequencing which you have, now you can actually relate and bring them closer. So that's more of like whatever was separated due to migrations, now you can again reunite all of those. Next comes down that you need to really take care of your age group and demography, and so if you are building on students, then students of what age group is a critical fact which you need to keep in mind. If you're doing something on diseases, then you need to also have that age group and the demography, because people under different socio-economic conditions will have different conditioning on how their face looks like, how they behave, and all of these. And these will be certain amount of biases which needs to be compensated in some way. The critical case over here which comes down is if you are trying to do a positive versus a negative. In that case, generally what you are suggested to do is that you need to have equal number of population. So the total number of positives should be equal to total number of negatives, and this is not that hard to understand why it is so. This is quite intuitive because it comes down from that whole point of entropy. So we generally wanted to have a point where my entropy of class distribution is maximum, and for any kind of a class distribution problem, my entropy is maximum when every class is equally likely, which is if there are n number of classes, then the probability of every class is 1 by n. That is the only condition when I will have the maximum entropy going down. And that's this whole implication which it brings over here, that you need to have equal number of subjects in each of whatever categories you are trying to do. So when we do it for medical images, I will come down to that whole lot of another 10 lectures around the different applications in medicine. Now that's where we have something which is called as a control group or a normal group, which is all healthy people who are devoid of a certain disease. But say here also comes an interesting point. So if I am trying to do something like you take brain scans, okay, or scans of the head, MR or CT or whatsoever, and then you are trying to find out whether somebody has some sort of a clot formation over there. Okay, now there would be people who would have clots, who are essentially who are the positive subjects over there. You need to take equal number of people who do not have clots. Okay. Now the point is that people who do not have clots does not necessarily mean that they are healthy. So what can happen is that there is another organ which is called as pituitary, which sits underneath the brain over there, which is essentially what is also called as the thermal regulator part of our body. So you feel cold or you feel hot essentially because of that pituitary. Now there might be issues with the pituitary. One of the things is pituitary inflammation. It may so happen that you don't have a clot in your brain, but you have a pituitary inflammation. So this becomes that a subject or a particular case which becomes control or negative or normal in one of the studies may become positive in the other study as well. And this is where you as a designer can really leverage this whole aspect in a significant way, because now you have an idea that you don't need to recreate the data set or acquire another new data set. You can actually use the same thing and do a lot many more experiments around with that itself. The next point is that sometimes you would be designing systems which have a prognosis or which follows up. Essentially there is a temporal nature which we are going to do. So that would be something like somebody has a lesion or some sort of a clot, and then you give some medicine and they are recovering over a period of time, and you would like to have that recovery tracked as well. Now these would be points where just a CNN like model is not going to work. So there would be something which we will do next week, which is called as a sequence modeling. So we bring in neural networks like recurrent neural networks, which essentially do a time series model, which are used for doing some sort of a series modeling, time series modeling, language modeling, and all of these. Now these are models which now will have to be integrated along with spatial models in order to create models which are spatio-temporal in nature, so that while you are changing across time scale, you can also have carry forward of all of these information and make an inference. Now where do you get all of this is a real critical point. Now the best way how we get to any of the data sets or anything is through papers essentially. That is one route, which is the classical very tested route of it. The new route is to go on to Kaggle, get down your data sets. So Kaggle is a very rich source of data sets, and that's how Microsoft really acquired it, because then they have a hold of all of these data sets itself in them. The next point where you can go is that at least for medical imaging, the field has been very cooperative in a sense that about a decade ago we decided that we will create a common consortia in the field where everybody will share their data sets and host challenges. So this is almost like a Kaggle of medical imaging, and the number of data sets and challenges we have hosted today, it outnumbers about 120 plus. So this is just a decade. In a decade we have done more than 120 challenges, and these are real large scale data sets. So if you start downloading any of the data sets, they are going to occupy something. The minimum one is about 3 gigs, and the max which we have seen is in the order of about 800 gigs. So that's close to a terabyte itself. Now that brings me to that website. So essentially, if you are interested really over here, this is a very good site to go and look into it, grindr-challenges.org. It keeps on updating. This is the oldest screenshot which I have. Today you have it for 2020, and there are 6 challenges from 2020 which are hosted. It's a real, and some of these challenges are such which have been hosted every year. So every year you see an update coming to the data set. So first year maybe there were 30 samples or something given. Next year, samples in sense like you would have volumetric data of MR or something. So each sample itself is about say 400 cross 400 cross 1000 voxels. So that's the dense samples which are available to you over there. So that brings me to this point of what is the major issue which we do over here in terms of validation, which is essentially called as an act of benchmarking. Okay. Now what is a benchmark? If I ask you this question, what is a benchmark? It's a standard English word. It does not have to do anything with your understanding of engineering. A benchmark is more primitive than the study of engineering and technology. So what is a benchmark? Benchmark according to an Oxford English Dictionary definition. You guys can Google up. I don't have any issues. Pull up your phones, Google up and see what is a benchmark. Google up, Wiki up, dictionary up, anything. Image search will also work. That will actually help you in understanding what is a benchmark much better. Search and tell me what is a benchmark. What's a benchmark? You got the definition from where? Kaggle or Quora? Stack Overflow? Benchmark. Hey, what is the classical like 1200s, 1300 AD definition of benchmark? Yes. So you remember in school you used to have one of these things where annually every year they would come down and measure your height and weight, and there used to be a scale pasted, a small tape like thing pasted on the wall. I mean in art school, like that was one of the arts and craft assignments given to us, which is like take your scale and put down all the marks on a strip of paper which needs to be half an inch apart, and then everybody will paste that one on top of the other, and you have a 4 feet or 5 feet scale created over there. So now that whole thing is what is called as a benchmark. Now benchmark is something which comes down from a artisan's bench, or you might have seen tailors who use a weird kind of they have scales which are like bent and crooked and everything. Have you seen a tailor actually do marking over there? Now they also have these kind of markings on their bench if you observe it carefully. So they would have a black cloth or something placed over there, and they would have white marks over there which are like standard feet marks, and 1 feet, quarter of a feet, half feet, like these different marks which they do over there, which are their ready references. So that's what's called as a benchmark. Now where this comes down is that if you look over here, this is essentially sort of like, this was a good example I found out of explaining benchmarks. So this is an original which is given down over there. This is what is expected. So this is the ground truth or the best case labels which are expected, humans have annotated. And what these are generating essentially are the different labels which each different algorithm is generating. Now here you have some of these numbers which come down, and how these are sorted is essentially based on some sort of a higher order in performance. Okay. So today what you call as a leaderboard, might have heard about this term, a leaderboard or a scoreboard for a particular challenge. So a leaderboard or a scoreboard is basically a form of a benchmark itself. So what it does is that there are different points across which you are getting compared. In leaderboard you will typically have multiple points on which you compare. In benchmark you will have only one metric or one point across which you are going to compare. So that becomes a linear scale, and you are basically located at one of these points which says that how good or how bad you are. Now that will help you in getting down like how, at what level from the top are you, in which quartile do you stand, are you there in the first quartile or third quartile, these kind of things which it will. So benchmarks are really critical. If you read any of the research papers, then you would find out that there would invariably be one particular tally table which will give out these benchmarks. Now in a lot of these cases, now coming to the point of something which was mentioned about baselines. Now baselines are essentially methods where you use all the vanilla techniques. So if I have a neural network to train and I am doing a classification engine over there, then what I would do is I will have a standard gradient descent, I will have a standard binary cross entropy loss function or a cross entropy loss function, and then I am going to report what this network is going to give. Now I can invent on a new kind of a loss function. So when I am proposing a new loss function, then I will have to show by proposing this new loss function how much did I gain. So how I can design an experiment is I can have 5 networks. On each network I apply the standard loss functions like binary cross entropy or negative log likelihood or etc., etc. And then I apply my loss function over here, that new loss function. And on each of them my objective would be that if I am really good, then for each of them my position should be better than each of their positions. Now this without the loss functions part, what you do is what is called as the baseline. So that's the datum reference. So if nothing new is provided over there, then how will it perform? When we put some interventions on top of it, how does it keep on growing? Now baselines can also be incremental. So there can be like 2 baselines, 3 baselines, etc., etc. So how that can be? So there can be one baseline which is where you have the network, you do it with binary cross entropy. Next you bring down weighted binary cross entropy. Next you bring down say weighted binary cross entropy plus mean square error. So these are different ways in which you are doing, but then everything was known. It's not like any of these loss functions were not known. So this was already well known within the practice. The only thing you are doing is you are just comparing and putting down that where do I fare with this one loss function? Is it intermediate to any of them or is it really better than any of them? That does not necessarily imply that every time you need to be better. You can be intermediately placed as well, and there can be different aspects around it. One aspect is like it is much faster to compute your loss function. It takes less number of flops. It's easier to get down a gradient of this loss function. The gradient is always continuous for your loss function. These can be different aspects on which you can always argue and pitch it forward. Now whenever you are doing any of these experiments, now experiments have different meanings for different people. Okay. So some experiments are like in case of deep learning, your training of a model and evaluating it is what is called as an experiment. But for people who are going to generate that data generates out of an experiment. So experiment is something which is again contextually very relevant over there. So what is where you are located? So if you are an experimentalist in terms of generating data, then that's an experiment which you are doing. It does not have to do anything with your deep learning over here. Okay. Now in that first case where you are essentially somebody who is generating the data, there are 2 different ways in which you generate data. One is what is called as a prospective generation, which essentially means that you know what is the hypothesis you are going to prove. So it's something like this, that you want to now make a deep learning engine which is going to tell you the gender and age of a person by looking at their face images. This is your hypothesis which you will have to test. So a prospective data collection, what it's going to do is, first you fix this is what I'm going to prove, then you ask somebody to collect the data. Now when you ask somebody to collect the data, you have certain constraints which you can now put down. So you can say, I want equal number of males and females from every age group I would need these many number of candidates in each class of male and female. Now, do I want that equally distributed, which is like if I want people in the age group of 30 to 40, then is it something I need one male face at 30, one female face at 30, one male face at 31, one female face at 31, or can it be something like 10 male faces in the age group of 30 to 40, 10 male faces in the age group of female faces in the age group of 30 to 40, and I am not really worried. So it can be like all the 30 male faces are at all the 10 male faces are at the age of 30, all the 10 female faces are at the age of 40. That can be a situation as well, which can happen. So until unless you really specify, you cannot. So prospective data collection is something which is going to let you do all of this so that you can test your hypothesis, which is over here. Now, the good pros or the advantages is that it can be very much class balanced and the whole distribution and highest entropy of data which you can collect. The cons is like it's generally costly to perform, and in health we have this major point of regulatory approvals, which means that if you are a patient who is going to give your data, then you will have to legally sign it off, because otherwise your data belongs to you. So if you get an X-ray done, the owner of that X-ray is not the hospital, not the doctor, but you as an individual. That's the law in India as of today. So the point is that if that's the case and you want to give your X-ray data to me, then it's your personal property which you are going to give me, then you will have to sign it off. So either I pay you to get that data, or you are going to just give it for some voluntary cause, so just as a donation over there. But remember that going with that same thing of data is the oil. So the data is your crude oil which you are standing on top of it. Now the next point is that crude oil does not burn. So if you want to make any use, then it's better that you actually start letting people refine that whole thing over there. Next comes this whole aspect of what is called as retrospective. Now retro is something which has happened in the past. So this is about all the data which is collected. So one example is tomorrow if you want to go and build some sort of face detectors or something using the images available with ERP. So ERP, everybody has a profile and you have uploaded a profile images. That is what is present in the ERP at any given point of time. Now ERP has this whole database of when this person's image, what is their gender and what is the age when this image was uploaded, that is available with them. Now this is a very good data set which can be used. The only issue is that by using this, you will be able to get down faces of people generally in the age group of 18 to 28. And beyond that are people who are professors and they are minority class over here. So the other part of it gets into a very much ill-balanced case over there. Now whatever you are going to do and build up, that is very good in this range of 18 to 28. But below 18 it will not be able to work out great. Above 28 also it will not be able to work out great because it has not seen enough of data in that particular one. So, but then the good thing is that you don't need to wait for long, you don't have a costly affair because everything is already there, it's already signed off. Now that's the advantage which you get, but then the cons is that you have your class imbalance issue which comes down over here. So these are again factors which you will have to really keep in mind when you are designing practical systems. So getting back to your sampling points, now for any kind of a data irrespective of prospective or retrospective, in prospective you can always ensure that you have this kind of a thing which comes down. So you have equal number of data, you have a very high variance in whatever data samples you are with, and that is going to help you build up a very reliable classifier. The point is when you have retrospective data available, by virtue of the fact that you have a lot of data available, now if for a certain class you have more amount of data points, just reduce, undersample that one, so that you can now match the statistics looking like this. So your situation ideally will be something like this, but now what you can do is from this particular one where you have more number of sample points, you reduce the number of samples points so that you can come up to this kind of a good distribution over there. So that's an engineering which you really have to do, and it's again something which cannot in general be automated. You have to look into it and do that. This requires a bit of domain expertise in order to work out. Now what we do typically in order to do that is you are going to figure out some ways of sample sufficiency. Now in health I was giving out this example that generally more people are healthy than abnormal, but the point is when you are healthy you never go for a scan. So how many of you would go for a brain scan or any part of the body scan if you are healthy? How many of you would go? How many of you go to the doctor when you are healthy? How many of you go to the dentist when you don't have a toothache? How many of you go to the optometrist when you don't have a vision problem? How many of you would go to an audiologist when you don't have a hearing problem? How many of you would go to an otolaryngologist when you don't have a throat or a ear problem? Nobody. It's the same way. You don't even go to the temple to visit God when you don't have a crisis. Right? So crisis is basically the divine way of bringing down subscriptions to the business model. Yes or no? And come on, I'm not speaking in anything weird. So the point is everything has a business model. So until you are in crisis, so if you never needed to study in order to have a job, you wouldn't even be studying. And if say like your companies would not really start asking you questions on deep learning, but rather be just looking at whether you have a deep learning foundation subject on your grade cards, then you guys wouldn't even be coming over here. Yes or no? Let's be very frank on this one. So because you are expecting some questions, so you are coming and attending to this class. Otherwise, who comes at morning? And that too like in the resumed winter as well. So that's the whole issue over here, that in most cases, though most people will be healthy, you will not be getting that data. And because there are no scans being taken down. And nobody really wants to get into a MR scanner when you are healthy in order to do that. Next is that there are a lot of these kind of rare cases which will come. In diseases, these are very unique. Anything which does not have anything to do with diseases, but has to do with say surveillance, with anomaly detection, with abnormality finding is also that. So one of these examples is that say you have a thermal power station somewhere and you put down a lot of sensors, vision based sensors and everything. The whole idea over here is to find if there is something which goes wrong. Now how many times would a thing go wrong in a thermal power station? What is the chance of something going wrong in a actual power plant? 1 in a year. Dude, then every year we will have one thermal power station blast off. It takes almost 10 to 15 years to create a thermal power station. I mean, ask this guy Vikas. He used to work just beside India's biggest nuclear power reactor in Kalpakkam. So if something goes wrong, then you basically wipe off a whole state of Tamil Nadu with that one. Have you heard about the Chernobyl incident? Very good. Have you heard about the Bhopal incident? Who is from Bhopal? Nobody in this class, unfortunately. We used to have a lot of people from Bhopal. But then you guys are like you were born after the incident. So you have just heard of it, you have not actually seen any part of it, neither was I. I was young. I mean, I had read in newspapers, that's what I remember. Now, the issue is that they are the rare class of things which will happen, and that's the most important class. So now comes the point that your positive class which you are trying to look has the least number of samples, then what do you do? So there will be some things to do around with sampling problems over here, or you will now have to train your models which now become very susceptible to any kind of an anomaly which comes, whatever does not match the normal kind of a distribution model over there. So this is like one but all kind of a problem. Anything which is not this class is essentially what is a threat to be. So they would need different kind of learning algorithms and cost functions which you bring over there. So this is what sums up over here. Now one thing is that you can always augment whichever is the minority class, you keep on upsampling that or bring in some sort of a distortion or something in order to do that. You can replicate samples from the weaker class, and that's something which has a term called as SMOT, synthetic minority oversampling technique, and it's a very commonly used. In fact, most toolboxes will have a SMOT calling function over there. So if you give down what is the ratio of the classes you have in the data set and what is your desired ratio of classes, it will generate sampling clone numbers over there. So essentially that sample will be cloned these many number of times so that you get a class balance. You can use any kind of these rotations, affine transformations, etc., and this is something which we had discussed while in the first few lectures on the data space of the problem, how you really overcome the challenges around with that. But then you also need to really restrict out on, if you're dealing with images, then how much you are warping and how much of intensity transforms you are applying. So you should not make something like, say in the handwritten digit recognition problem, we had the digits in black written on a white background. But now if you do a intensity transformation by just flipping it, which is negating it, so white digits in black background, then the same model will really find it difficult to work it out. So these are challenges which you will now really have to look into to addressing. Now in any kind of a problem, so we did look into the class of problems which were essentially classification type. So you are just going to give out one label. Now there is another class of a problem which we are just going to do after this, which is what is called as a segmentation problem or a semantic segmentation in our case. Now what segmentation essentially means is that every single pixel will have a class label. So instead of the whole image getting a class label, you will have a class label associated with every single pixel. Now when you do that, then the metrics or the loss functions for that really differ in a significant way. One way is you can always say that because it's a classification on a pixel level, then let us take binary cross entropy on a pixel level. You can do that. But then there are other methods for which we do it. Now typically say this is your input image, this is your ground truth which I call as this set A, and this is the output of your CNN for doing this kind of a segmentation which we call as the set B. Okay. Now the whole point is that if I want to find out how good or bad they are. Now one thing can be which is called as an overt segmentation, which is essentially this one is, so whatever is the output is bigger than whatever is the ground truth which is expected. So what this is doing essentially is it's telling a lot many things which are not to be present over here. Say the white part is what is my positive class. So it has a lot of false positives which will come in over here. So the samples which are actually not positive, but you are telling them as false positive. Now that thing is what is called as an overt segmentation error, and it's a very simple set theory or a Boolean arithmetic which it does essentially. So this is, you take this particular class, whatever is there, and have an intersection with the complement of this ground truth class. So that is essentially going to give you all the pixels which are not present in the ground truth, but have been marked as positive, and divided by the total number of samples in the ground truth, which is a normalization factor, so that bigger ones will have a bigger numerator, but then you will need to compensate with the denominator as well. Now similarly under segmentation is all of those pixels which are in the ground truth, but you have marked them as not presenting to the ground truth. That's where it becomes a B complementary, and then you divide by A in order to do this balancing. Next, this is what is called as a dice coefficient. Now a dice coefficient is essentially whatever is sort of a idea about the intersection, which is how much are the two segmentations overlapping across each other divided by the sum total of the area over there. Okay. Now the point is that in case both of them overlap together, then mod A is equal to mod B. So that would make this 2, but then A intersection B and a mod of that is the same as mod of A. So that is going to be in the best case as half, and that's the reason why you have this 2 given down over there, so that you range limit this one to a 0 to 1 kind of a case. Next comes down this which is called as a Jaccard coefficient. Then Jaccard coefficient, you have intersection divided by union. So in case there is a perfect segmentation, then whatever is the intersection is equal to mod A is equal to mod B is equal to this union as well. And that's the reason when you will get down a unity case. Now these all costs are essentially limited to 0 to 1. In fact, for your dice and Jaccard, you also have differentiable costs available. So dice itself is a loss which is very commonly used in semantic segmentation kind of problems itself. Now another interesting point which we do in segmentations is you get down that whole block over there, but then in the block you have what you have found out is basically whatever is the impact with the area, but you did not find out what is the impact with the boundary happening over there or whatever is the contour. Now typically we have this kind of a distance which is called as a Hausdorff distance. Now Hausdorff distance is sort of which finds out what is the maximum value of the closest 2 points between the contours. So what it does is something like this. So say I have a point on this contour which is over here. Okay. Now for this point, this is what my segmentation has given me. This is what my input ground truth is. Now for this point, how close, what is the closest distance to the closest point on this curve? Now that is essentially this point. Okay. Now that I get this particular point over here, I will start doing the same thing over and over for all of them. Now similarly, what is say the point over here, which is the closest point to this curve, that is essentially this line. So similarly, you can have different ones. So based on which is your reference and which is not your reference, you can always keep on finding that one. Now these distances are standard Euclidean distances which you do. So what you are doing over here essentially is you find out which is the closest point over here, and then you find out what is the maximum distance between the closest points over here. Now by doing this closest point, you are essentially aligning two curves. You have two curves, you are essentially aligning them, how they would align very easily, and now you find out what is the maximum misalignment error which will come down over here. Now this whole thing is not a range limited function in any way, because it's a distance measure in Euclidean, so it can have any value greater than 0. The only point is that it will be a value greater than 0. There is no upper bound on this one. Next comes our point on classification, which is you can apply that on semantic segmentations, you can apply that on normal digit classification or anything. Now you have one part which is called as a ground truth, and that will have a positive class and a negative class. Okay, so if I have just a 2-class problem, whatever I am predicting will also get a positive class and a negative class. Now anything which is marked as positive and you predict as positive is a true positive. Anything which is marked as negative, you predict as negative is a true negative. And so on and so forth, you get down these points. So a false negative is essentially anything which is not negative, but you have annotated as negative. A false positive is similarly anything which is not positive, but you have annotated as positive. From there you get down these metrics coming down. Now accuracy is something which you generally report, but this has a problem to bias. The point is, if there is one particular class which is say 80% or 90%, and if you are correctly predicting on that class, then you would see that you would get a very high accuracy. So take an example like this, that I have 90% which belongs to negative class, 10% which belongs to positive class, and somehow all the 100% of the samples got predicted as negative class. Then anyways my accuracy is still at 90%. Now that does not give me an indication that I made a horrible mistake in my positive class. Okay. Now do you think this can have a very dangerous implication in real life? Yes, but essentially I will tell you there is this bias in medicine is exactly opposite to this one. Okay. And this is what all of you have faced. So when at the start of February, how many of you had cold, cough, blocked nose and everything? How many? Only 1, 2, 3. Array, raise your hand. Everybody has it. Okay. So how many of you of them went down to how many? The rest of you guys are healthy? Pretty healthy. Awesome. You guys are really becoming immune. Maybe you guys should be recruited to be sent to fight the coronavirus. So now, so what do you do when you get this cough and cold? What did you do? Nothing? Nobody went to BC Roy? No, because that is my example of telling you bias, understanding that whole part of what can happen. Now in general, when you have all of this and you go to BC Roy, or another standard thing which happens in BC Roy is during the exam time. A lot of people will undergo stress, and because of that they will have loose motion. A standard stomachache problem, something around it, and you go to BC Roy. They have a standard set of medicines even before you come. So it's like if you are at BC Roy at morning 7 o'clock to any time by 9:30, then they will have a standard dosage of medicine which they will write and give it to you. So that will have an aspirin, that will have a digestive, that will have a liver relaxant. That before you tell, you would see that most of the time the doctor actually starts writing it down. Okay. Now there is a bias with this. The bias is something like this, that majority of the people who come down over there will have this problem. So if we give medicines, we are going to cure majority of the people, but then the risk is that there would be a minority, 2 or 3 people who might not come with this problem, who might have a very different problem, and you suddenly give it to them. Now they get into that risk over there. Okay. So one classical example is is there anybody who is allergic to coffee? I mean, people have something called as a caffeine allergy as well, or allergic to milk products, lactose intolerance, 1%, 2 people, 3 people. Yeah. So similarly, you also have a caffeine intolerance. So I am a borderline caffeine intolerant person. The worst case is that I cannot drink Javan coffee. The best kind of a coffee, I cannot drink that because I am intolerant to that particular kind of a coffee. So if I drink coffee, accidentally I drank that particular one, which is going to give me that, and I will have a mandatorily I will have a cramped stomach. So I will start getting cramps. Now if I go down at that same point of time, the guy at BC Roy most likely will end up writing aspirin for me. Coffee and aspirin makes a very deadly concoction. Never try to do that. So never try to have coffee and aspirin or coffee and paracetamol, which means that any caffeinated product, which is don't even try to drink paracetamol with Pepsi. You are almost at the verge of like dying because of dehydration because of this particular experiment. Now if that gets taken over there, then the risk which I will have on my life is significantly high. So now the issue is that how do we really capture all of these ones which are related to the minority class, and that's where comes in all of these points, the other metrics. Now out of these metrics, a very critical metric is what is called as an F-score, and F-score by virtue of all of this essentially something which is agnostic to the class distribution. So you can have a 90:10 distribution, but if you are systematically making errors on this 10% of the population, then this F-score significantly goes down. And that is what you would have wanted. You would have wanted to be more cautious on this lower minority class of the population and not get swayed by the majority class of the population. Now that's something really interesting to look into, how these metrics are designed in order to do that. So that brings to the next part of a thing which is called as a receiver operating characteristics. Has anybody heard of this term before? It was in mid-sem syllabus, okay. So you more or less know about receiver operating characteristics over there, great. Now the point is that when you are trying to do all of this, then comes this major part which is essentially your folded cross validation. Now in folded cross validation, what you are going to do is critically very important. Now this is where sets you apart from all of them. So essentially you have the different number of classes which is given to you, and now what you will have to do is that you will have to divide your whole data set into number of subsets such that you are going to do your experiments. Okay. So the next assignments which we will start writing after this, the coding assignments, will be the same on that MNIST whatever you have done, but then you have come to a form of like this is my batch size and this is my learning rate and this is my loss function. This is what you have done in that assignment. Next is what I would be asking you is that do a 10-fold cross validation and tell what is the range of variation which will happen in your performance. Now when you want to do that in a 10-fold manner, what that would imply is that you need to divide your data set into 10 small subsets. Now when doing that, if you have something like you have all number zeros in one data set, all number ones in another data set, that can be one way of dividing it into 10 data sets. But then if you train a model with that, what is it going to learn? It does not have the other classes in it. So it will not learn anything. Then how do I do? You would ideally assume that all data sets have all classes, but then you also need to put down the fact that if there are 6,000 samples for 10 classes over here, then they are basically 1:1:1 in how it's divided, or a probability of 1:1/10. Now that would also imply that in your test data sets or trained data sets, whatever you are creating, they also have the same kind of a ratio. So in order to do that, what we typically do is, if I have a 2-class problem or even an n-class problem, you essentially divide them into that many number of sets. So that's why doing this kind of a breaking over here. So this part of the breaking is what we call as bags. So the ideal form is that you create 10 bags over here. In the first fold, you take bag number 1 for your testing, bag number 2 to 10 for your training. In the next fold, you take bag number 2 for testing, bag number 1 and 3 to 10 for your training, and so on and so forth. You keep on going over here completely. So that's going to help you come down, and as a result what you will get is you will get these F scores or any of these points for each of these folds, and then you report this variation. So now coming back to the first question which I had asked you, like how will you find out whether your model has a 10% variation in performance? That comes down as a result of this one. And now there is a famous statistical proof which we are not going to cover over here, but you can look into William Barrett's paper on large scale experiments from 1916. It's a paper in the Journal of the Royal Statistical Society. So there is a whole proof which he has done on, like, if you extend this to large number of samples, then whatever is the total variation in the population is something which you can get by doing a tenfold cross validation itself. And that's the reason why most people would stick to a tenfold cross validation for reporting. Today we have even brought it down to fivefold cross validation with a 2% chance of error in predictions. So that's where this first part of it stops. We will take a 5 minutes break and then we come back and do the semantic segmentations.